Magnetic Materials Assignment Help. For any help regarding magnetic materials assignment help, visit https://www.eduassignmenthelp.com. Email info@eduassignmenthelp.com. Call us at +1 678 648 4277. Problem 1.1. Assume that an interface, similar to that sketched in Figure 2.7b but with m/10 equals 1 m equals m, is carrying a current 0, 0, j, y equals 2j 0, y/h plus 1/2, and h is not necessarily small. 20a. Sketch the dependence of the current density on y, b. What are the boundary conditions on an h field, h, y high, y 0, across the interface? C. Sketch your result and x. Justify it in terms of the field generated by the current distribution. Make sure your result behaves properly as h approaches 0. 1.2. You need to make an electromagnet that produces a field of 0.6 T in a 1 cm gap. You use a rectangular core design, 20 cm 10 yen cm with the gap on one of the 20 cm legs. You make the core out of soft iron with R is almost equal to 100. The yoke has cross-sectional 2 area equals 10 centimeters. A. If you are able to conveniently wind 600 turns of copper wire on the 20 centimeters leg, how much current will you need to achieve B equals 0.6 T in the gap? Neglect edge effects. B. What is the flux density in the iron core at this current? 1.3. Consider a permanent dipole magnet with its north pole a distance h away from a sheet of copper. Calculate the magnetic field in the copper and sketch the field in and near the copper sheet when it carries no current and when it carries a uniform current I0 out of the plane of the figure as sketched below. eduassignmenthelp.com. 1.4. Describe the energy required to move a demagnetized ferromagnetic sample from -infinity toward a permanent magnetic dipole at the origin having its north pole pointed toward the ferromagnet. Include the effects of magnetization of the sample and its energy in the dipole field. Then, assuming you can hold the magnetization fixed, remove the magnetized sample back to -infinity considering only its energy in the dipole field is changing. What is the energy change in this second process? How do these energies relate to a 1 and a? 1.5. Derive EQ 2.30 by eliminating high from the two expressions that led to EQ 2.16. 1.6. Verify that EQ 2.45 satisfies Laplace's EQ 2.48. 1.7. You formulate a new soft ferrite composition and want to test its low-field magnetic properties. You sinter a toroid and a rod from your new proprietary composition. The figures below depict the BH loops you observe on each. eduassignmenthelp.com. A. What is the remanent induction in each case? B. What is the coercivity in each case? C. Approximate the effective permeability in each case for a drive field of 2 OE. D. Assume B equals H plus 4 pm is almost equal to 4 pm and use M equals CH with EQ 2.29 to estimate the demagnetization factor, N, for the rod. E. Use Table 2.1 to estimate the demagnetization factor of the rod-shaped sample which you measure to have an aspect ratio of 10:1. eduassignmenthelp.com. 1.8. You need to calculate the magnetic field parallel to and outside a strip of a permanent magnet of length L. Assume that M is uniform inside the magnet. The strip is L/5 wide, perpendicular to the plane of the figure below, and L/200 thick, in the direction below, and you need to know the field at heights of 0.05 L and 0.3 L for 0x less than L. Use a three-dimensional formula, EQ 2.45, for the field assuming that the width is small relative to the length, i.e., the strip acts like a rod, and also use EQ 2.3 for a two-dimensional approximation, ignoring the field spread perpendicular to the plane of the paper. The form of the x dependence of Hx is as important as the magnitude of the field. eduassignmenthelp.com 1.1a B. For the normal component of H, it is still possible to use the boundary condition derived for normal induction. It does not depend on surface current, but only on permeability. Solution. eduassignmenthelp.com From EQ 2.4, boundary conditions may be derived for H, integral H. dl equals integral J. Xd setting up these integrals gives, the length of the path is L, its height, H. Where, for the LHS, the one goes counterclockwise about the path of integration. How does H vary through the surface layer? It is necessary only to take different X limits on the Y integrations, enclosing less of the sheet current to see that H varies X linearly from its value at H/2 to that at H/2. High, on the other hand, is discontinuous at Y equals 0 C. The X component of H1 exceeds the X component of H2 by the amount of J0 H/2. Combining this with the above condition on the Y component gives eduassignmenthelp.com. The decrease in H in medium 2 is consistent with the direction of the magnetic field X produced by the surface current as shown above, center. That field augments H in X medium 1 and tends to cancel H in medium 2. The variation of H through the current X sheet is shown at right. 1.2 Want B equals F/A equals 0.6 T in the gap of the circuit. A. How much current is required in the N equals 600 turns on the 20 cm leg? Assume the area over through which the flux passes in each leg of the circuit is the same. It is also sufficient to assume that the 600 turns act over the entire length of the circuit. Then, in the first term of the sum M equals 100. The second term is for the length of the circuit in R. The gap, R equals 1. Here it is assumed the area over which the flux spreads in the gap, AG, is 2 the same as AI equals 10 to 3 M. Thus the required current is, notice that the larger term in the sum is that due to the gap. If the magnetic circuit were 10 centimeters long rather than 60, the gap would make up 90% of the reluctance, and for a 0.6 T gap field, Ni equals 0.011 asterisk 0.6/M. In this case, I equals 8A. eduassignmenthelp.com. B. The flux density in the iron core is given by solving the above Ni equation for F/A, Fe. Because we have assumed the same area throughout the circuit, the flux density in the iron would also be 0.6 T. If we were to account for the fact that in the gap the flux spreads out over a larger area, then the flux density in the iron would have to be greater than 0.6 T to maintain 0.6 T in the gap. Alternatively, if you calculated the H field created by the coil H equals Ni/L equals 12.9 Ca/M. The demagnetizing factor reduces the effective permeability to about 60 from 100. Then inside the iron B equals M cent MH equals 0.97 I. This large R0 value reflects the fact that to get 0.6 T in the gap, B in the iron must be higher due to flux spreading in the gap. 1.3 From EQ 2.51 and using where X is the distance along the copper sheet, it follows. The field lines shear to the right above and below the CU sheet as you get closer to it. This is caused by the addition of the field due to the current and the field due to the dipole. The tension in these flux lines produces a force on the sheet to the left. 1.4 Start with a sample of soft ferromagnetic material at Z equals -infinity and a permanent magnet at the origin, see Fig. below. Bring the soft magnet toward the origin, step 1 in figure, and two things happen as it moves into the dipole field given by EQ 2.51. eduassignmenthelp.com. First, the sample